This video focuses on the concept of relative motion. And the key behind the concept of relative motion is that all motion is dependent on a frame of reference. A frame of reference can be anything, from the earth to a flowing river, the air surrounding an airplane, to a moving sidewalk. Sometimes the frame of reference is stationary, and sometimes it is moving. A specific type of a frame of reference is called an inertial frame of reference. An inertial frame of reference, or inertial reference frame, is one that is moving at a constant velocity. In other words, the acceleration of the reference frame is equal to 0. So next we're going to look at a question. If a car is driving at a constant velocity of 50 kilometers per hour due east, is that the velocity that we always measure? It may seem like the answer should be yes, but think about it this way. Let's say that you're driving beside that car, and you are traveling at 60 kilometers per hour. It seems as though that car is going much slower than you. You would not measure the speed to be 50 kilometers per hour. Instead, you would measure the speed to be only 10 kilometers per hour. Or here's another example. Let's say that you're moving near the car, but in the opposite direction. If you were moving in the opposite direction of the car, you wouldn't measure its speed to be 50 kilometers per hour. Instead, it would seem like it was going much faster than that. So no, we do not always measure the velocity of the car to be 50 kilometers per hour. It is dependent on our frame of reference. As we analyze problems dealing with relative motion, we will always be looking at two different frames of reference. And so there's an equation that we can use to help us determine how fast something is moving relative to a given reference frame. That equation says that the velocity of our object relative to reference frame B is equal to the velocity of our object relative to reference frame A plus the velocity of reference frame A relative to reference frame B. In each case with these problems, our reference frames will be something different. So let's take a look at exactly what these reference frames could possibly be by looking at our first example problem here. In this problem, Rafi is pulling a toy wagon through the neighborhood. He's pulling it at a speed of 0.75 meters per second, and there happens to be a caterpillar in that wagon that's crawling toward the rear of the wagon at a rate of 2 centimeters per second. What is the caterpillar's velocity relative to the ground? When we analyze relative motion problems, we always want to identify what is the object, what is reference frame A, and what is reference frame B. In this, it wants to know what is the caterpillar's velocity. So the caterpillar is our object. That means that our other objects must be reference frames. So we have a wagon and the ground. It doesn't matter if you made A the wagon or the ground. No matter what, you should get the same answer. Okay, so looking at what we are given, we know that we are searching for the caterpillar's velocity relative to the ground. That's the velocity of the object relative to reference frame B. We're given two other speeds. It says that the toy wagon is being pulled through the neighborhood at a speed of 0.75 meters per second. Well, that's the velocity of A, but it must be relative to something. In this case, that's the velocity of the wagon relative to the ground, which we called B. Then we're also told that there's a caterpillar in the wagon, and it's crawling toward the rear of the wagon at a rate of 2 centimeters per second. Well, we know that can't be the speed of the caterpillar relative to the ground. That's what we're looking for. So that's the speed of the caterpillar relative to the wagon. Now, all I've done is written down the numbers that are given to me in the problem, but I've paid some attention to which variable corresponds to which number. I also need to pay attention to units and direction. Your units should always match. Looking at these values I have here, I have meters per second and centimeters per second, so my values don't match. I'm going to convert to meters per second, which gives me 0.02 meters per second. I also need to pay attention to direction. The caterpillar and the wagon are not moving in the same direction because it tells me the caterpillar is crawling toward the rear of the wagon. So I will make its velocity negative. Now I can plug things into my equation that I'm given, that the velocity of our object relative to reference frame B, or the velocity of the caterpillar relative to the ground, is equal to the velocity of the object relative to reference frame A, plus the velocity of reference frame A relative to reference frame B. Now I can just plug in the numbers that I have, negative 0.02 meters per second, plus 0.75 meters per second, and I see that I get 0.73 meters per second. The direction is forward, or the same direction as the wagon was moving. This next problem is very similar. It talks about riding a bus. This is a problem that I would like you to complete on your own and bring to class tomorrow, showing that you have watched this video and hopefully understand the concept of relative motion. Pause the video now and try it. Example 14 is slightly different than the past two. In this one, you'll notice that we have some directions added in here. An airplane is flying due north relative to the air, 150 kilometers per hour, but there's a wind blowing 75 kilometers per hour east. What is the plane's speed relative to the ground? To think about a problem like this, I think about what is actually happening. This plane is heading north. It's facing north, it's trying to fly north. But there's this very, very strong wind that is pushing it east. It's not going to end up flying north. Instead, it's going to end up going at some angle between north and east. If we were observing it from the ground, we would notice that it's not flying directly north. Because we have north and we have east, we're going to have to do a little bit more with vectors to solve this problem. But as we did with that first one, we're going to start off identifying what our object is, what reference frame A is, and what reference frame B is. Our object is the plane. I can tell that from the phrase, what is the plane's speed relative to the ground? So relative to the always indicates a reference frame. Whereas when I'm talking about an object's speed, we know that's the object. I have two reference frames here, the air and the ground. So those are my three objects, my three things that I have here. Now let's look at what we're given. It says the airplane's speed relative to the air is 150 kilometers per hour north. It also says that the wind, that's the air, is blowing at 75 kilometers per hour east relative to the ground. That's the velocity of the air relative to the ground, or VAB. By the way, the order of the variables right here is actually important. It's the velocity of A relative to B, not the velocity of B relative to A. It does make some difference as to which reference frame you set to being A and which one you set to being B. Often, if the ground is one of your reference frames, it'll go in as reference frame B. Okay, it wants to know the plane's speed, velocity of the object, relative to the ground. Now, because these two vectors are perpendicular, I cannot simply add 150 and 75. Rather, I have to add them as vectors. I'll start by writing out my equation. The thing I'm looking for, the velocity of the plane relative to the ground, is the velocity of the plane relative to the air plus the velocity of the air relative to the ground. So I'm adding together these two vectors. And as we learned when we were first learning vectors, we must add these vectors by drawing them tip to tail. So my first vector, 150 kilometers per hour north, looks something like that. And my second vector, 75 kilometers per hour east, looks something like that. So my resultant, the thing that I am looking for, is that purple vector you see there. This top here is 75 kilometers per hour. Over here is 150 kilometers per hour. So I will use the Pythagorean theorem to find my resultant. Using the Pythagorean theorem, I find that my resultant is 167.7 kilometers per hour. This problem says, what is the plane's speed? So I don't need to worry about direction. I only need to worry about speed. Relative to the ground, the plane is traveling 167.7 kilometers per hour. Just in case you're curious, if the problem had said, what is the plane's velocity relative to the ground, I would also use trig to solve for this angle right here.